there's some similarity between thermosiphon and heat pipe, but heat pipe can work against the gravity also. Thermosiphon needs the help of gravity to bring the liquid condensate down, whereas the liquid condensate can be pumped up by the heat pipe. So this is because of the wick structure. So these things we understood, but exactly how a wick functions, how is it able to do this, that we don't understand so far. Okay, and let's see a little bit about heat pipe.
ATS has released their newest family of products and services, flat and round heat pipes with heat pipe design services. Heat pipes are closed evaporator condenser systems with a very high heat flux transport capability. Heat pipes consist of an evaporator, an adiabatic section, and a condenser section. Various working fluids are used in a heat pipe to transport the heat energy. Generally, the type of working fluid determines the heat transport capability. Finally, a heat pipe includes a wick. The working fluid is returned from the condenser to the evaporator via capillary action through a heat pipe's wick. Homogeneous wicks are constructed of one type of material or machining technique. Examples include wrapped screen, sintered powdered metal, axial groove, and many others. ATS's off-the-shelf heat pipes use both sintered powder metal and grooved wicks because they are cost-effective and provide high thermal conductivity. ATS's sintered powder metal heat pipes have the added advantage of being able to handle high heat fluxes and deployment in any orientation, even against gravity. ATS Design Services can custom develop heat pipe solutions including both homogeneous and composite wicks depending on the application. The choice of fluid depends on what operating range the heat pipe needs to function in and the metal which the heat pipe is made of. Water has a useful operating range of 30 to 200 degrees C, ammonia has a useful operating range of 60 to 100 degrees C, sodium has a useful operating range of 600 to 1200 degrees C. ATS uses distilled water in their off-the-shelf flat and round heat pipes as it is cost-effective and can be used in a wide temperature range. For more extreme temperature ranges, ATS has experience with mercury, methanol, liquid ammonia, and other working fluids they can design with. While application determines fluid types, which fluid is the most common? Cooling Zone ran an engineering poll in April 2014 and found the top 3 fluid types to be water, liquid ammonia, and methanol. Heat pipes can be fabricated from various material types that are compatible with the working fluids being used. Proper material choices reduces the chance for working fluid and material interaction, heat pipe degradation, and failure. Material types include copper, aluminum, and stainless steel. This list shows some of the compatible material and working fluid combinations. ATS's flat and round heat pipes are made of copper to cover the broadest temperature range with a cost-effective solution. ATS can design with other metals and advise customers on application-specific solutions with careful consideration for the cost-benefit trade-offs, the materials, and working fluids. Heat pipes come in various shapes and sizes, though the most common are either round or flat heat pipes. Heat pipes can be bent as required for both system and thermal requirements. Round heat pipes are generally used for transferring heat energy from one point to another. Flat heat pipes, also known as vapor chambers, work conceptually the same as round heat pipes, but their shape allows for different applications. Applications can include embedded heat pipes and heat sinks, such as ATS's MaxiFlow heatsink family or ATS's pushpin heatsink family, laptop computers, embedded heat pipes for single-board computers, military applications, RF, telecommunications applications, and server cloud computing. Heat pipes work as follows. Heat applied externally to the evaporator section is conducted through the pipe wall and wick structure, where it vaporizes the working fluid. The resulting vapor pressure drives the vapor through the adiabatic section to the condenser, where the vapor condenses, releasing its latent heat of vaporization to the provided heat sink. The capillary pressure created by the menisci in the wick pumps the condensed fluid back to the evaporator section. Therefore, the heat pipe can continuously transport the latent heat of vaporization from the evaporator to the condenser section. This process will continue as long as there is a sufficient capillary pressure to drive the condensate back to the evaporator. ATS brings their strengths in test, analysis, qualification, and design services to their heat pipe line. ATS's heat pipes are tested in their own thermal lab, resulting in data that ATS publishes based on their own characterizations. For applications, ATS Design Services offers a complete solution from testing through prototypes. ATS's MaxiFlow heatsink and pushpin heatsinks can both be deployed as the condenser, making the heat pipe solution even more efficient. For more information on ATS's heat pipes and heat pipe solutions, please visit qats.com or email us at ats-hq@qats.com.
Okay, as you can see, this is a company presentation. So they are advertising their products. Ignore that part of it. But I had shown you this because it has nice photographs and a general overview of heat pipes. I don't know how much difficulty you face in understanding their English, but you can, even if you follow the photos, that is reasonably good. Right, so I want to also show you this one. This is better because this is what I'm going to show you now. Gives some demonstrations of heat pipes. Last video was just kind of an overview of a product, but here this person is going to also talk to us about effective thermal conductivity of heat pipes, because effective thermal conductivity of heat pipes is much larger than thermal conductivity of the best metal that you can think of. So copper is about 400 watt per meter Kelvin. This is much higher than copper effectively. I mean, this is not a single piece of metal or anything like that. This has this chamber in it, and it has got wick in it. So we don't talk about a thermal conductivity directly. We talk about an effective thermal conductivity. That is very high for heat pipes. So he does some comparison in this particular video and talks about this high effective thermal conductivity.
Hey everyone, today I'm going to be showing you the world's fastest heat conducting material. And then I'm going to cut it open and show you what's inside of it and how it actually conducts heat so fast. So first let me show you how fast this thing actually conducts heat. It's pretty amazing. It's almost instantaneous. I have two rods here. One of these is just a regular copper rod. Now copper has a very high thermal conductivity. It's one of the fastest conducting metals there is. And because electrical conductivity and thermal conductivity are related to each other, that's why you see a lot of wires made out of copper, because it can also transfer electricity easily. So I'll compare this copper rod to this heat pipe here and show you how much faster this heat pipe actually conducts heat compared to this copper rod. Okay, so now we're going to try to actually see this heat transfer. So I'll put my copper pipe right here, and then I'll put my heat pipe on the other side here. So when this stuff gets cold, it turns black. So we should be able to easily see the heat transfer from the pipe to the ice when I stick ice on both the copper pipe and the heat pipe. Okay, so what I'm going to do is I'm going to set ice on the heat pipe and the copper pipe, and we're going to see how fast the heat gets transferred from the pipe to the ice. Okay, 3, 2, 1. Whoa, it just instantly turned it black here. And now you can see it slowly moving up the copper pipe. That is awesome. You can see how long it takes to move up the copper pipe. Okay, we've heated both of them up now. Let's set our ice on. Okay, 3, 2, 1. Look how fast this one turned black. The heat pipe was almost instant. And then the copper pipe, you can see the heat slowly coming out of it. So what's really neat with this is by just using the heat in your hand, you can actually cut through ice like it's a razor blade. Look at that. So in doing that, it instantly gets cold in my hand. So I have to try to transfer the heat back into it as it cuts through the ice. But it's so cool how it instantly just cuts into the ice when I touch it to it. So this is just using my own body heat to cut through this. This isn't heated at all. Look at that. So let's cut this open and see why this can transfer heat so much faster than a regular copper rod. This can actually transfer heat around 2 orders of magnitude faster than a copper rod. So copper can transfer heat at around 0.4 kilowatts per meter Kelvin, and this heat pipe can transfer at 100 kilowatts per meter Kelvin. So what's a little bit scary about this is, as I'm cutting it, it's going to generate heat, but it conducts heat so fast that it'll probably burn me. So I'm going to wear some gloves while I hold this. Okay, so inside of here, it just looks like a hollow copper pipe. But let's look closer and see what we can see in here. Okay, so I've split open the end and bent it down here. So you can see the inside of it. It's not just like a smooth copper pipe inside of it, but it's actually really spongy. So the sides of the wall here are almost like it's a sponge. And the reason that that's in there, because inside of this, there is actually a little bit of water. And usually what they'll do is they'll get a regular copper pipe and they'll fill it with a little bit of water, and then they'll let that water boil, and then they'll seal off both ends of the pipe. So that all that's left in there once it's sealed off and cools down is a tiny little bit of pure water in a vacuum. And so there's a really low pressure in there because the water that was hot vapor condenses down once it cools down, but the ends are sealed, and so basically you just get a drop in pressure and a tiny little bit of condensed water. And the spongy inside of the pipe is so that the water can get wicked up onto the sides of all of the pipes. So then how this heat pipe actually works is it's made of copper, and so you still get the copper conduction itself. But the magic comes from the water vapor inside of it. So the tube starts off at a very low pressure, but as you heat up one end of it, the water that is at that end of the pipe heats up. And when it heats up, it vaporizes. And as it vaporizes, the pressure increases. And if the other end is colder, then that means that there's a pressure force driving that water vapor to the other side. So at high pressure over here, low pressure over here, and so all of that water vapor gets pushed to that side. But now the other side is colder, and so the water vapor now condenses. And so basically you get this fast push of water vapor to the other side, and then it condenses. And so it takes heat from this side and quickly pushes it to the other side. And so that quick heat transfer comes from the heat it takes to vaporize the water, and then it puts that heat back on the other side when that water condenses. And so it's this continually efficient heat pump that continually takes heat from one end of the pipe and pushes it to the other side of the pipe. And you can actually use different types of liquids and different kinds of metals for this, but this copper-water combination actually works extremely well. These are used in a lot of applications, including inside of computers. When you need to transfer a lot of heat quickly, these heat pipes are unmatchable with any other standard metal. And I'd like to thank Brilliant for sponsoring this video. Brilliant's Daily Challenges helps make learning a daily habit. Every day they publish several challenges that provide a quick and exciting view into math, logic, science, engineering, and computer science. Each of these daily challenges provides you with the context and framework that you need to tackle it, so that you learn the concepts by applying them. And then if you like the challenge and want to learn more, there's a course quiz associated with each challenge that explores the same concepts in greater detail. If you like my channel and like the stuff you learned on it, then head over to Brilliant to sign up for free. But if you'd like to sign up for their premium subscription, then click the link in my description for 20% off of their premium subscription. Hey everybody, thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, hit the subscribe button and hit that bell so that you can be notified when my latest video's out. And check out theactionlab.com to see the Action Lab subscription box. And I'll put a link in my description as well so you can see the Action Lab experiment book. And thanks for watching, and I'll see you next time.
Okay, so this is also a public domain video. I got it on YouTube, the last one. And this I already told you about. Even he talks about this sort of structure in the video itself. I mentioned this, that okay, this is the wick, the dark circles that you see. This can be the wick. You can imagine this to be the wires in a mesh. Okay, screen. Wrapped screen is one structure of the wick. So you can think of this as the wires in a wrapped screen, or it can even be sintered metal. So there are solids and in between there are gaps, right? The one which he cut, so he took this heat pipe and he cut it, then he opened this one, right? So what sort of wick did it have? Sintered metal, right? Now, this kind of structure, what I mentioned last time is that there is a difference in radius of curvature between the evaporator side and the condenser side. Okay. Now, why is there a difference? Because from here, a lot of liquid is getting evaporated, because this is in the hot end of the heat pipe. And whereas on this side, vapor is getting condensed because it's on the cold end of the heat pipe, right? So that's why there is a difference in radius of curvature. Ultimately, this difference in radius of curvature leads to movement of liquid through the wick, and this is the physics that we have to understand. Okay, to do that, let's understand this surface tension thing a little bit better. So you have, I think you probably have some background of surface tension. You might have studied it in physics in school and also in undergraduate. Undergraduate fluid mechanics, I don't know whether it's covered always or not. Sometimes it can be covered, sometimes it may not be covered. Is surface tension in the GATE syllabus? Is there? Okay. Yeah. So let's try to understand this. So let's say you have a vapor bubble in liquid, and the vapor bubble is assumed to be spherical. So cut this in half, so you get this hemisphere. Okay, and there will be a force at the circumference. This circle, on this circle, there will be some vertical forces. So that is due to surface tension. How do we write surface tension? We write this as some sigma, which is related to surface tension, multiplied by the circumference, which is 2 pi r. What is r? R is this radius. Okay, so this is the force which is going upwards. Now, when it comes to pressure, okay, there is some pressure inside and there is some pressure outside. So P1, this is Roman 1. So we are saying that in this is 1 and this is the outside is 2. Outside is 2. What's inside? Vapor. Outside is liquid. Now, so there is this pressure. Okay, there is pressure from outside also. So the actually what we get is, if we take the difference of these two pressures, because we are projecting on this plane. Okay, so we can take the difference of these two pressures, multiply it by pi r square to get the pressure force. Is that okay? Yeah, so that should equal sigma times 2 pi r, isn't it? So the force due to surface tension goes up along the circumference, So that is F is sigma times 2 pi r, as we saw in the last slide, right? So that's equal to this P1 minus P2 times pi r squared. So P1 minus P2 is this P1 minus P2 is sigma 2 pi r divided by pi r square, which is 2 sigma by r. Okay, 2 sigma by r. This has a name. This is called a Young-Laplace equation for a sphere. Okay, so you should know the name also, because if somebody asks you what is the Young-Laplace equation, you should be able to locate this equation. Now, the other thing that you can see from here is that the internal pressure, the inside pressure is greater than the outside pressure. Correct? Inside the vapor. And the balance is because of that surface tension. So sigma and r, these are positive values. So if the radius is small, if this is a tiny sphere, then the difference in pressure is actually higher. Correct? Smaller is r, larger is this difference in pressure, P1 minus P2. Okay, so this is some understanding that you have to carry with yourself. This you have seen, this one, this sphere bubble, this you have seen. Okay, right. So I'm going a little faster because I think you know most of these things, but let's see this also. This is a nice video. So we got these 4 tubes. Okay, and we'll keep water at the bottom and then see what happens if we insert these tubes in that water. You know what's going to happen, right? The water is going to rise up. So let's just see that. Yeah. So the tube that you see on the left, that is of diameter 0.6 mm, and the one on the right is 0.15 mm. So the narrowest tube is on the right, and in the narrowest tube you get the maximum height of the liquid column. Okay, that's expected, right? Okay, now this is capillary rise. So I found out, I didn't know this before, but I learned that capillary comes from a Latin word which is capillus, which means hair. Latin is like an ancient language, like Sanskrit. Okay? So a lot of English words can come from Latin roots or Greek roots or whatever. So this is like a hair. So what does that mean? It means a capillary tube is actually a narrow tube, because we are talking about hair, so very thin. Okay, so capillary effect is a consequence of surface tension, and if you have a smaller diameter tube, then the rise is higher. Also, some examples: if you place a cotton wick in kerosene reservoir, then the kerosene will rise up the wick. Okay? So in a candle, what happens is that because of the presence of the flame, the wax melts and then it gives you a liquid wax pool, which will, because of capillary effect, rise using that wick. Okay, that's a very important phenomenon, because since it rises, it comes in the vicinity of the flame, and that liquid can, from the wick, it can evaporate and then go to the flame and burn. Right, so that is one. It's also responsible for rise of water in trees. Okay, trees also have this kind of capillary sort of structure, so water from the ground can rise up to the upper parts of the tree, to the various branches. And this I told you previously, it's a curved free surface of a liquid is called meniscus. Now this is a book, this is an undergraduate book which has some discussion on this. So I mentioned this also. There is a book by Chengel and Simbala, fluid mechanics. So Yunus Chengel has some books on various subjects like thermodynamics, fluid mechanics, heat transfer. You must have seen those books. Okay. So this is written as a Chengel, but this C is written with some accent at the bottom. So he's actually Turkish. He came to visit IIT Delhi a few years back. So this is, even though it's written with a C, it's pronounced like Chengel. Okay. And you also know about a contact angle, and contact angle is like if you have less than 90 degree, then the liquid is said to wet the surface, and more than 90 degree means it's not wetting the surface. So for water in glass, the angle is not very high. So this is a photo which Chengel has in his book. So you can see that this is a 4 millimeter inner diameter glass tube, and there's a little bit of curvature, but that it's really not much. Okay. So what is happening is water is drawn up because there are forces. There are two kinds of forces that we can think of. So there is if you think of a liquid surface like this, then liquid molecules have forces amongst themselves. Okay? And there are also forces between the liquid molecules and the solid. Right? So because this tends to go like this, we understand that the adhesion forces between the solid and the liquid, that is able to do this in spite of the cohesive forces between liquid molecules. Correct? So cohesive forces are forces between like molecules, similar molecules, so between water and water molecules. And adhesive forces are between unlike molecules, that means water and glass. And the relative magnitudes of these forces, they determine whether a liquid wets a solid surface or not. So water is going up, so obviously there is strength in these adhesive forces, and it's actually these adhesive forces winning over cohesive forces. And if you have a narrower tube, then it's more effective. But it doesn't, for all fluids, it doesn't need to go up, because there can be, in case of some fluids, there can be capillary fall also. There need not be capillary rise always. Capillary rise in the left figure for water is again taken from Chengel's book, and mercury, there is a capillary drop. Okay. And capillary rise is inversely proportional to the radius of the tube, and capillary effect for water is usually negligible for tubes where the diameter is more than 1 centimeter. So the photo that we saw from Chengel's book, what was the diameter? 4 mm. right? So there you can see a little bit of capillary action, a little bit of contact angle. But in large tubes, that effect is not much. Okay, so if we use manometers, then you need to have sufficiently large tubes so that the capillary effect is not much. Okay, so let's understand this a little bit better. So we saw that spherical bubble in liquid, but this is also going to be important. So we have to understand this. This is capillary rise, and from this we can go to understand what happens in a wick. Okay, so this again you might have seen. So these are, you can see, like in that video, these are tubes of different diameters. So this is the narrowest diameter, narrowest tube, and then the height of the capillary rise is more in this case. Okay. Now, if you want to analyze this, then we will mark this one. So this is marked 1, this is marked 3, this is 2, this is again 1. Okay. And this height is h. What is this force? F. F is along the tangent to that curved surface, right? So this is due to surface tension, obviously. Now, we will also say that this radius is r. So r is not the radius of curvature of this curved surface. R is the radius of the tube. Okay. And we also say that this P1 will be equal to P3, correct? P1 is equal to P3 because they're at the same level. So if we say that this P1 is atmospheric pressure, then this is also atmospheric pressure, right? And this one, number 1, okay, is this going to have the same pressure as this one? Well, approximately. Actually, if you think about pressure, then this thing is at a height compared to this level. So there can be a little bit of difference, but that's a column of air, which is, whose density is low. So we can safely say that this pressure and this pressure, these two things are equal, right? And so we are saying P3 equal to P1 because they're at the same level, right? So P1 is equal to P3. And let's see whether you understand this or not. So Fy will be sigma times 2 pi r but cos theta. So this is this theta which we are calling a contact angle, right? So this is all right. And we also have the weight of this column. That is pi r square h, because this is the cross-sectional area is pi r square, multiplied by h is the volume, multiplied by density is the mass, then multiplied by g is the weight, right? So that rho pi r square h g is the weight of this portion of the liquid above the bulk liquid level. So above this level we have this much liquid which has got this weight, right? So this weight is balanced by this force, which is arising because of surface tension, correct? So this tells you that rho gh is, okay, you divide by pi r square on this side, so you get 2 sigma cos theta by r. So you can also see that h will be larger if you have smaller value of r. So that's why that explains why liquid should go up a larger height if you have a narrower tube. So we understand this, and we also know that P3 minus P2 is rho GH, correct? This is using this column only, hydrostatic pressure drop. So if you come here, this is a higher pressure. If you go up, the pressure actually comes down. And we already had rho GH is equal to 2 sigma cos theta by R. And we have P3 minus P2 as rho GH, but P3 is equal to P1, correct? So P1 minus P2 is 2 sigma cos theta by R. P1 minus P2. So P1 minus P2 is interesting because this is across an interface, right? So they are kind of at the same level, but they don't have the same pressure. Why? Because the surface tension and the contact angle, these things have created a pressure difference between the air outside and the liquid that is at a lower, on the other side of the interface, right? So P1 minus P2 is 2 sigma cos theta by R. So the pressure which we are getting immediately below the interface is lower than the atmospheric pressure. Okay. And surface tension is basically, we understand the surface tension is causing the pressure to drop from P1 to P2. So this is lower pressure. Okay. What will that do? That will, and this is lower pressure, outside is higher pressure, P1 is higher, so the liquid gets pulled. Liquid will get pulled. So this drop in pressure results in the higher pressure affecting the liquid column to go up, right? So it pulls the liquid so that you get this column. And how much will it pull? What will be the height h? It is until it finds this kind of balance, until it balances all the forces. So this is what is happening due to surface tension. We called this the capillary rise. And of course, this angle is called contact angle. The contact angle is important, and this is the angle on in the liquid side. So this is liquid. This is the angle on the liquid side between the vapor liquid interface and the solid surface. So solid surface is this, and vapor liquid interface is here. You draw a tangent to the vapor liquid interface. The tangent makes an angle theta with the solid surface there. So that theta is a contact angle, which you're writing here. Theta less than 90 degree is, if it is less than 90 degree, we say that the liquid is wetting. And when theta is between 90 and 180, you say that the liquid is non-wetting. So contact angle is an index of the wettability of the liquid. So wettability is actually a term, is a technical term, is a scientific term. So this contact angle varies with solid materials. So all these things depend on combinations, right? It depends on the liquid-solid combination that we are talking about. So the contact angle of water on a gold surface is 0. While the contact angle of water on Teflon is 112 degree. 112 degree means it's more than 90 degree. So it's non-wetting, correct? More than 90 degrees non-wetting. And this is a nice photo which I got from some book. Okay, I think it's a book by Petrucci. Okay, so this is water, and you can see that it's got this sort of a contact angle, and this is mercury. So look at the surface curvature. So this is like this, concave, and this is convex, right? So you must have seen these things yourself in various applications. So wetting fluids will have cos theta value that will be positive because theta is less than 90 degree. So cos theta is positive. And this results in positive capillary pressure that moves the liquid. And non-wetting fluids will have cos theta values that are negative because theta is more than 90 degree. And this results in negative capillary pressure that creates a suction force on the wick. The liquid will then be prevented from moving to the evaporator. You need to, from condenser, you need to move the fluid to the evaporator, right? So the working fluid in heat pipes must be wetting fluids. So you choose the liquid and solid combination in such a way that you get good capillary force. So good movement of the liquid there. All right, and capillary pressure, capillary pressure, which this is the delta P, which is P vapor minus P liquid, can also be written as sigma times 1 over R1 plus 1 over R2, where R1 and R2 are the principal radii of curvature. This is for a general surface. So there is a surface like this. So there can be an R1, there can be an R2. So this is like geometrical concepts. Fortunately, when we talk about something like this, the two principal radii of curvature are going to be the same. Okay, so you don't have to bother that much about it. And principal radii of curvature, they look like this, but we are talking about this one. So R1 equal to R2. Okay, and this R1 equal to R2 also R1 equal to R2 is also equal to R over cos theta. What is R? R is that tube radius, right? So how do you get this? I hope this is not difficult to see. So you just think about something like this. Okay, so this angle is how much? This angle. Talking about this angle. How much is that? Theta, correct? Because you have this one as theta, so this must be 90 minus theta, right? This one, so this must be again theta, right? So this is theta, and if this is theta, we know this is capital R. The capital R cos theta is small r, which is what we are writing here. So this I still thought of showing you this one because sometimes there can be, in your mind, there can be some confusion between, the capital R and the small r, right? But we will be working mostly with this pore radius. This is a tube radius, but when we go to heat pipe, this will be like a pore radius, pore. This is the pore radius, right? That's like we saw these things, right? We saw these, and we saw curvature like this here. So this is, we can think of this like a pore area, which is kind of like these tubes. Okay, so this is broadly what happens, but I'll just touch upon this thing a little bit. Now this we'll have to take up on Friday, but complete analysis will take up on Friday. But just observe what happens on the left hand side, which is evaporator, and what happens on the right hand side, which is the condenser. Okay, so the contact angles are not the same, right? And this is some radius of curvature that we has marked. Actually, this is not. This one is radius of the pore on the evaporator side. This is radius of the pore on the condenser side. Okay, these are contact angles. So there is variation between these two. So we have to understand why that causes this liquid to flow in this direction. Okay. So it will be a kind of a simple calculation which is based on the concepts that we discussed today. So ultimately, what did we discuss? We said that this pressure and this pressure, these two pressures are not the same, right? So that's one important thing. Why are they different? Because of surface tension, isn't it? Capillary effect, right? And which pressure is higher, which pressure is lower? This pressure is higher, isn't it? This pressure is lower. So this sort of concept will, and we could quantify also. We could quantify the difference between P1 and P2. And we could write it in terms of sigma, we could write it also in terms of the contact angle, correct? We have done that. But there is going to be difference in the contact angles between the evaporator side and the condenser side. So we have to put all these together and see what is the driving force for liquid flow. So we'll have to do that. Since we don't have time today, we'll have to do that in the next class on Friday. Thank you.